So I'm so excited to have Rhys here with us this week. So Dave's a consulting geologist based in Vancouver with a focus on advanced projects and active mining operations. And he'll be chatting to us today about the importance of field observations and constraining the structural interpretation of ore deposits. So thank you so much, Dave, for joining us. I'm so pumped that you're here.
Thanks very much, Jess. Let me just get this presentation up and running here. So again, thanks very much, Jess, for the invitation here. It's been a great series you've had, and as I was mentioning to you when we were setting this up, I tried to set this presentation to really follow on some of the previous ones, including the good ones from Sally Goodman and Brett Davis. And also Greg Morrison's presentation too has some links here as well, because I'll just be talking about how, we might be able to code some of the structural features we're going to talk about here in drill core, and then how to use those in modeling. So first slide here, just the intro here, you can see the transition you have to go through when you're doing exploration. On the left, the conditions in Africa when it's over 40 degrees and you are more tempted to spray yourself down than the core, but then what you look at can be quite complicated, and sometimes not even more complicated than when actually you see this ultimately underground on the right. So you really have to go from that stage to the stage on the right, and that's really what I'm going to talk about today, is showing you some field relationships which have implications from when you're interpreting drill core to how you actually take that and you put it into a model for a deposit. So of course, these days, data is becoming more and more important. As we're going to deposits that are harder to find, that are not necessarily exposed at surface, like you see in the upper right, we're going to deposits that really are largely blind. And so the more data we can use, the more data we can get that is relevant, the more we can better understand deposits. And you can see on the lower right here, I've shown an image of a real database, and this is unsubdivided, and you can see the mass you get on a stereo net when you plot that up. There's really nothing you can see in that data set that's going to help you model anything. But nonetheless, some people would put a contouring program onto that. They get a cluster in the middle here, and then they'd model everything parallel to that. You really don't want to be doing that. So that's what we're going to talk about a bit here today. There's also a growing separation too between geologists collecting the data and those who are interpreting it. And really, you want to have that ideal mixture of both, where people are also interpreting the data they collect, because that way it leads to better data collection when you can see what information you're collecting, how it actually manifests itself in a deposit. There's new tools such as Televiewer, which can lead to massive collections of data, which can actually obscure the real important features in a database. So you have to really make an effort to be pulling out the key features and subdividing your data appropriately to make a database that's actually usable. So if you oversimplify it, you're going to get a plot like you have on the lower right. You can also over subdivide it, but at least when you subdivide things more than less, you can bring things back together and look at different types of structural features together. So really, it's all about appropriately coding your structures and consistently coding them between geologists. So we're going to go through a few examples of some structural features that you could code in different ways and how to interpret them, and also some other features which aren't even data-based, which are important structural aspects to look at in drill core. So here's examples of why this is important. You can see I've got here a stereo net of data obtained from oriented drill core. And you can see on the left is an approach that a lot of people take. They plot a stereo net, they get a cluster, they get a single contouring peak, and then on the lower left, they model everything parallel to it. And that is an incorrect answer, because you can see, first of all, that the data has a huge amount of spread to it. From the top of the stereo net to the bottom, there's a change in strike and dip of over 90 degrees. And so this data has a huge range within it. So if we were to appropriately code the data, we might see something like you see on the upper right. where the large cluster on the bottom that people were modeling parallel to on the left is actually set to smaller veins associated with an ore body, which actually has quite a different orientation and consists in cross-section here of some shear veins, which is the things you really want to model because the extension veins on the tips are parallel to them overall if you take an overall surface that would envelop them completely. They're sitting within a mafic intrusion, which if you just did not subdivide your rock units, you wouldn't even see. So they're preferentially occurring within that intrusion. And you can see on the stereonet above here that the clustering of the main shear veins is a much smaller set than you have of the extension veins. That's because there's fewer of them. There's just lots more extension veins than there are shear veins. You'll also see too another important feature, shear zone on mafic contact I've shown here, which is really telling you the contacts of this mafic unit are taking up some slip. There's actually veins forming along those, but it's telling us where those shear zones are that are also feeding into the shear veins. So you also can see here too in the upper right, I've got some structures which aren't even related to the mineralization. These are later structures, calcite bearing veins, but if everything's coded as veins, you don't have the benefit of seeing that. So by subdividing your structural data, you can come up with a model like you see on the lower right, which is a classic model for a lot of orogenic gold deposits. Wallaby in Western Australia, for example, would be an example of this type of geometry. So to gather this type of data, there's a number of tools that have come along in the last few years. I mean, some people still remember the spear and the clay method and so forth for orienting core years back. But about 10, 20 years ago, Easy Mark in the lower left was the common method, where you essentially had this tool which had ball bearings in a fluid here, which would align to the gravitationally lowest part of the drill hole. And then all these pins on the end could be linked to the core in the core barrel. Today, we have some better digital technology where we can align the entire core barrel. The two most commonly used are the ACT tool and the true core of bore long ear. So these allow us, of course, to orient the core tube and then get the core in it oriented with a mark on the end, which we can carry down the core, such as you see on the left. So there's many core shacks I know all around the world who are operating this way, but some parts of the world we're just transitioning to this kind of technology. So you can see here, there's an Ori mark in the drill core with a mark on it from the drillers, which then with a angle iron, you can align your core with arrows on the pointing down hole and ticks pointing down hole and draw that line through core in that same run, and then try and align it with the next run. And if it doesn't align, you can record that as a lock angle and use that as a QA/QC method to understand how accurate or how between different runs is your structural measurements. Once you've done that and you have your orientation, you can either start to measure that data using this alpha beta method with various tools that I'll show on the next page, or you can go the older way was to take the core and reorient it in a rocket launcher or a goniometer and directly measure it, orienting that goniometer to true north and making sure there's nothing magnetic around to screw up your measurements. Once you take your core for alpha beta measurement, then here are some of the tools that you can use to get those different measurements where you're measuring the alpha angle being the core axis angle and the beta angle being the position around the drill core and around the circumference of the core from where the ellipse on the bottom of the feature makes going clockwise around the core. So with those two measurements, we can use software to recalculate what the orientations of those features are. Or you can use something like the Reflex IQ logger on the lower right to directly measure from core, and it will directly calculate what the orientations of the features are that you are highlighting with your laser pointer. And of course, you have to do this with a Vancouver Canucks pad underneath here for it to work properly. So other features that are important to measure are the beta and gamma methods for lineations, and you can read Tom Blankensoff's 2015 paper if you want to do that. I'm not going to go through the methodology of doing all the alpha beta calculations. It's just really to show you some of the methodology because I wanted to talk about where the errors can come in this sequence. The other technique that can be used today is the Televiewer, which is a CCD camera lowered down a finished drill hole, producing 360-degree imagery down the drill hole that is oriented. Now, this technology can work very well, particularly if you have the time to really get good imagery down a hole and the hole is clean, plus there's good contrast between features in the drill core. But often those conditions are not met, and you can actually get some very poor imagery. And also the other thing that a lot of people aren't aware of is that with the Televiewer imagery, oftentimes structural features that are less than about 20 degrees to the core axis are extremely difficult to see in the imagery. And as a result, you get a bit of an accentuated orientation bias where you can't actually see or measure many of those features, particularly if they're low contrast. The other thing too is that there's also an offset between the position in the drill core and the position in the imagery, which can be up to a few meters. So you have to correlate, so you have to find in the imagery a feature that's going to correlate with the drill core. And the other issue too is that oftentimes this imagery is interpreted off-site by a technician, not by the geologist as part of the group of the exploration team. So the problem is then you are going to get a whole series of codes and figures out of this, which may not correlate with the structural features you know and work with, in part because the technician doesn't know the geology, and secondly, because they cannot distinguish it in the imagery. So the best way to use this imagery is actually to lay out core side by side with these images, and then take marks and put them on the imagery. So either the geologist who's working with that or the technician who's using the software can then take those marks and the codes the geologist assigns and actually assign a proper code to each orientation that they obtain from the Televiewer. So I've got here a little bit of a list of some of the different things that can go right or wrong during the different stages of oriented core. Of course, drilling stage is stage one, and potential problems include the fact that the tool may not be properly aligned, the drillers don't use it properly or misuse it. It's a premature for some things like easy mark, firing of the tool and so forth. And in fixing that issue in quality control, you really need to train the drillers. It's been a long haul here in North America to do so because the drillers haven't been used to it. But in Australia and Africa, drillers have been doing this for years, and a lot of the data is very, very good. There was actually some case I came across a few years ago where the drillers were faking the mark because they didn't want to do it. And we discovered this because we found the tool sitting in the core shack and the drillers hadn't even taken it to the rig. So there's been a lot of reluctance to adopt this by some drillers, but this issue under the quality control with drilling is improving everywhere. It's always going to be an issue, of course, if you have very bad ground. It's very hard to get good through-going orientations in drill core. Then the next step that you potentially have issues with is the marking of the reference line. If the core is not properly aligned, the mark is drawn between broken areas, so it doesn't really align. You also need to, of course, to help deal with this issue, use an angle line iron to lay out all the core where you can. Don't mark the line while the core is in the box. And record the lock angle between the different different drill runs. If there's a difference in the position of the reference line, how much is it? So you can actually get a better idea of how different runs correlate to each other. Then there's the stage of structural data collection. Now, this is really what I'm going to talk about in this talk and focusing on the next part of the talk here. Essentially, this is the geologist side now, when you're actually gathering the data from the drill core. And once you've dealt with all the QA/QC issues of the drilling and marking of the reference line, this becomes the main issue is whether or not your data is going to be useful in modeling and in creating an appropriate database for geotechnical work and other sides as well. You really need to subdivide the data properly. It's just like mapping. You know, if you're underground and you're mapping, if you can't recognize features in underground that to distinguish different types of veins and so forth, you're not going to be able to do it in drill core. So really, you need to be setting clear conventions. You have to have proper coding and so forth. You need to recognize big structures versus small structures, really break out things appropriately and relevantly, and don't overmeasure data that really isn't going to help you, because you can, again, not see the forest for the trees. You can end up with that stereo that I showed on the second slide. Then we go to the next step, which is the use of the data in modeling. And so part of that comes down to quality of the data itself. You want to use some of the better data, of course, if you have a low lock angle and you can say that the data is correlating between runs. But the other aspect here is the important data, as I mentioned, is diluted, not properly coded, and faults are often overinterpreted. So from the QA/QC sense, the data, look for what we call donuts. I'll show you the next slide, where the common orientations or common structural features rotate around the drill hole in a small circle, suggesting that the reference line on the core is not consistent between runs. So then you look at the data. Do the patterns look real? Is everything clustering around the drill hole? Are there certain clusters that are independent of drill run that look to really be clusters of independent types of structures? And so to help with that, it's often the geologist that's gathering the data, as I mentioned earlier, that is actually best qualified to actually do the interpretation, or to sit down with the person doing the modeling and point out key structural features to help with that model. So here's some of the QA/QC issues that you can encounter. So here we have on a stereo at a drill hole, and you can see a ring of structural data rotating around that stereo net, suggesting that what this ring of data is showing you is the rotation of the reference line due to error in the drill hole. So it's basically spinning around and your structural feature is spinning with it, giving you that ring in the drill hole. And the key of that is to see that is that the drill hole will lie in the middle of the ring. So if you plotted the drill hole on a stereo net, that's where it's going to lie. So you're going to get a ring around it. This was a project a few years back I worked up in Northern Canada, where what we did is we basically tagged common structural feature, which was foliation in this case, by drill run, and you could see that rotation. Each run has a different cluster. So at least each cluster you can see is consistent, but it was rotating around the drill hole. So in a case like this, if you have a consistent foliation, even if you have a problem like this, you can recognize this. You can take that cluster of data, and if this is what it should be over the left, you can actually rotate that back, and other structural features you've actually measured, you can rotate back with it, and you can use that data as long as you have a consistent structural feature to work with. So you can actually overcome some of those issues in some cases by using a known structural feature to reorient your core back to where it should lie in the cluster on the left. The other thing that often happens when you're dealing with structural data is if drill holes are all drilled the same direction, you can have some fairly significant orientation bias. You can see on the upper left here, there's a little bit of a sketch showing a vertical drill hole intersecting structures of two different orientations. The steep structures you can see here are barely intersected, but the ones that have a more gentle dip to them are intersected far more frequently. So right away, you can see that you're going to get an orientation bias in your structural data to the more gently dipping points. Now, you can weight that, use the Terzaghi weighting method to basically look at what the predicted number or frequency of orientations are in the drill hole, and take points that are less frequent and elevate their relative abundance on a stereo net for contouring purposes. And really try and overcome that orientation bias. But the problem with this is you can actually induce further bias by doing that if those features that you're trying to elevate in their importance are actually really quite rare. So you got to be very careful in doing that. The better way is to just drill holes of different orientation. And that way, if you're not always drilling parallel holes, you're going to sample orientations much more representatively than you are if you're just drilling with one single orientation. The other thing that can happen is if you drill all your holes the same way, as you can see in the lower left here, here's a sterionet that shows the orientation of a series of drill holes. You can see how well they're clustered. And on the left is the orientations plotted from these drill holes of veins from a deposit that I worked on. And you can see that all of the data clusters around the orientations of the drill holes. Well, it turns out that this is orientation bias. This is exactly what we're seeing on the left here. And so what has happened is that we've got, in this case, a series of veins which aren't that consistently oriented. They're not quite a stockwork, but they have quite a bit of range in their orientations. And because of this bias here, the ones that are almost perpendicular to the drill hole are being sampled in their orientations much more than the ones that are at a low core axis angle. And what you're getting is a cluster around the drill hole. Now, the problem with this is people will often look at that sterionet and say, look, that structural features are really clustering well. That must be the real orientation. Well, what you're doing is creating a confirmation bias, where you're thinking now that that really is the orientation of the features in the drill hole, when it isn't. Again, going back to the upper right and drilling holes with different orientations is a good way to test this. And one thing I'll often do when looking at structural data from drill core is if all the data plots with the same cluster as the drill hole, I start to get suspicious. I want to see clusters up here or over here or in different positions, because that's telling me that clearly that is not an orientation bias coming from the drill hole. It's separate. So those are key things you want to look for when you're looking at oriented core data. And you want to do this early in your program, because if you drill off a deposit or you drill off an exploration program and you do this after the fact, you may realize that you've got to go back and drill some more holes, or you may model things incorrectly because you think you've got the orientation nailed down when in reality you've actually got confirmation bias and an artifact in the data. So now I'm going to talk more about structural features and how to subdivide them, and also how to potentially interpret some of them in this context as well. So you can see in these images here, we've got on the left a ductile shear zone with a nice quartz vein associated with it, and on the right a brittle fault. Now, a lot of people, when they're logging core, will call the shear zone on the left and the fault on the right all faults. Now, if you do that, you're actually coding the same code for structures that are totally unrelated to one another. Because you can see on the left here, these shear zones here are associated with white mica, iron carbonate alteration, semi-brittle to ductile deformation. This is deformation and structures that are forming at 300 to 350 degrees Celsius. Versus on the right, this brittle fault has low temperature clay. It's very brittle. It's got no veining, got no alteration, less than 200 degrees Celsius. It's a late retrograde feature. It's come in way after the fact. It's got nothing to do with these structures, except in some places, these brittle faults might exploit the older shear zones. So you get a coincidence of the two structures, but you really need to be coding these types of structures completely differently. They're not the same feature. And if you join them together in a model, you're joining up the wrong things. So you can actually model things incorrectly. So here's an important diagram in that regard, in that this shows what structures do with depths, with geothermal gradient, or with in a metamorphic belt, where the deeper you get in these belts and the higher you get up on the geothermal gradient and the hotter it gets, basically the structural style changes in ore controlling structures as you go deeper. So near surface, below temperatures of about 300 degrees Celsius, things are brittle. Okay, and you get gouges near surface like we saw before, or you can get a little bit deeper down what we call foliated cataclasites. These are cohesive, but still fault breccia rocks. They're behaving brittly. But you, at 300 degrees Celsius, what you do is transition across a boundary where quartz starts to behave in a crystal plastic manner. This is where we start to get ductile deformation in the rocks. You can get ductile deformation a little higher too if you have weak minerals, if you have phyllosilicates, for example, and slip along their surfaces. But the transition to quartz is really where a major change starts to occur. But in this range, between 300 to just over 450, we are in a range now where quartz is behaving ductilely, but feldspar starts to behave ductilely at about 450 degrees. So what that means is if you have a quartz-rich rock interlayered with the feldspar-rich rock, the feldspar-rich rock is going to behave in a brittle manner, and the quartz-rich rock is going to behave in a semi-brittle or ductile manner. So what we get is what we call rheological contrast, and that's evidenced, for example, in the boudinage you see in the upper right of the image here, where we have a feldspathic unit, a dike, which is becoming boudinage. It's behaving in a brittle manner and being wrapped around by the foliation in the host rock, which is a quartz-rich schist. And so if you were to drill a hole across that, the center of that boudin, what you would see is a rock in the middle that is the feldspar-rich one that doesn't look deformed at all, but the rock around it, which is just schist, is going to have a strong foliation. So some people would make the interpretation that the feldspathic rock came in after the deformation, but you can see macroscopically that's not the case at all. They're just deforming in a different manner. So you got to be really careful with that interpretation. What's the importance of that? Well, you can see in the lower right that when we have vein systems forming in orogenic gold districts, that rheological contrast can cause the focus of sets of veins in the brittle unit versus the rock around it when it's behaving in a more ductile manner. So on a larger scale, entire ore bodies can look like this. This is the scale of a single mining face, but entire ore bodies over 50 to 100 meter wide intrusive bodies can localize this way and have highly focused areas of mineralization. So when you're seeing these areas of metamorphism and deformation, typically you're going to go through a cycle like this. You're going to start off with this line representing time. So in the upper left, you're starting off here with a cold rock prior to metamorphism and deformation. Deformation and metamorphism occurring hand in hand in an orogenic belt will drive that rock down through hotter and hotter conditions, more ductile conditions, and then after the peak metamorphism and peak of deformation, you may go into a retrograde conditions and exhumation. And so when you go from prograde to peak, what you do is you deform the whole rock mass and metamorphose the whole rock mass. All older structures become basically, if anything was brittle there, it gets overprinted by ductile, it recrystallizes. And so what you end up with is a ductile rock with semi-brittle shear zones, which then starts to go into retrograde conditions and exhumation. And gradually, as it becomes exhumed, later deformation events will be progressively brittle. So typically, when you're looking at a rock, the structures you're going to see always form a retrograde sequence because they're basically the older ones that predate the peak of metamorphism have been overprinted by the peak metamorphic assemblages, but all the other structures you're going to see are the progression from that peak downward to cooler and cooler temperatures. So basically brittle rocks up here are typically late, ductile ones are typically early, and that's the typical cycle you're going to see. So always it's important to think of that when you're looking at particularly orogenic gold districts, that if you start trying to interpret brittle faults as being related to mineralization, you're probably going to be wrong unless they're just exploiting older structures, and then they themselves aren't actually the controlling structure to mineralization. Another very important feature from a structural sense, which is often not recorded when people are just doing core orientation, is Younging directions in stratigraphy. Most common being graded bedding and turbidite sequences. Very, very important. this way you can start to sort out folds. If you have orogenic gold deposits, then these can interact with folds. Thrusts can be associated, which repeat stratigraphy, and you can only know that often if you're looking at drill core, if you've got Younging directions to show that. You can, in outcrop and sometimes in drill core, you can actually make out pillow Younging directions too in these pillowed mafic volcanics, where the arcuate portion of the pillow is the portion that's up sequence. It's the youngest part, because the bottom of the pillow deposits on the irregular topography created by previous pillows underneath you. In some drill holes, you can see that. It's often difficult in others, but the other way too is that often a pillowed flow will have at its bottom a more gabbroic base and have a finer grain top, so you can actually get coarse grading in these. So basically getting the stratigraphic tops allows you to really look at the bigger picture structural architecture in the deposit, which is going to potentially control where your mineralization may lie. And here's a good example of this. So on the left, what I'm showing is a fold and thrust belt in the Alps, a modern fold and thrust belt. This is what we call thin skin deformation, where we're taking panels of sediments and we're imbricating them on a series of thrusts that are coming off a basal thrust surface here. And when this type of fold and thrust belt is then metamorphosed, as we see in a lot of Archean belts or Proterozoic belts that have undergone green schist or higher grade metamorphism. All of these low angle thrusts get tilted upward into steep orientations. And in this case, in the upper right, this is a schematic section through the Porcupine Basin, the Timmins area, with the Younging directions I've measured from graded bedding, showing that there are younging outward from the core here. So these sediments in the middle, which are the youngest rocks, are actually in the middle of the anticline where you expect the oldest rocks to be. So what this is called is an inverted basin. And these thrusts you see here may have started off as normal faults that were the basin boundary faults to begin with, but they are inverted during the major fold thrust event. And why is this important? Well, in all of these areas, there's gold deposits, and the gold deposits are localizing on the positions of some of these older faults, particularly where they're favorably oriented. And to give you an idea of how subtle some of these things can be in drill core, if you don't know that they're there, this image in the middle is of that pipestone fault you see up the upper right there. And this is a view looking the opposite direction, but on the right is the Porcupine sediments, less than 2685 million years old, with a Younging direction to the left, which is to the north. And on the left, these are the Kidd Munro volcanics, which are much older. So the sediments are younging towards the volcanics, which means the area of that pen is a major older thrust. But it doesn't look like anything, really. It's got a little ductile shear zone on it. But think of it like this thrust fault here you see on the left in the Alps, which might have just had a narrow band of gouge on it, but still might have had, over 10 kilometers, 15 kilometers displacement on it. Faults don't have to be thick in the brittle regime to accommodate a lot of displacement. And when you deform them under ductile conditions, they can get even narrower. So this structure here, if you didn't know it, you might miss it, but it actually has probably more than 10 kilometers of displacement on it, and it's the width of that pen. Very, very important. The only way you're going to know that is establishing those Younging directions and really figuring it out. Here's another one of those types of thrusts in the lower right. This is area B, you see on the diagram up here. And you can see there's a carbonaceous breccia, which has flattened fragments in it here. This is also another situation where the sediments to the north, you can see here just getting disrupted as they approach that feature, are Younging to the south towards the mafics, which are older than them. Therefore, the mafics are sitting structurally on top of them. And here again, we're in a situation where there has to be more than 5 kilometers displacement on that breccia there, which is only about 20 centimeters thick. That could have started off as a clay gouge, like along one of these thrusts right here. So very, very important to recognize these geological relationships. So, and here I've taken an image where we've got what you could see in a drill hole. And this is what you're going to see. You're restricted in drill core. You always want to see outcrops where you can, because this illustrates the problem of interpreting drill core. So this is a little sliver I've taken from that outcrop on the left with the red line. So here you can see how if you just try to interpret the orientation of the metamorphic layering here, the original stratigraphy, you would probably try and measure a core axis angle like this parallel when I'm showing S1 there. But you can see on the left, that is actually not the orientation of stratigraphy at all. Stratigraphy is folded back and forth and has actually been reoriented in many segments and transposed into parallelism with this second foliation. So what you're actually measuring is the second foliation. There are hints though in here, as you can see in this piece of core right here, which is just from the same area, that you could see potential for this kind of a folding to have occurred. You can see in this little sliver I have here, there are little fold hinges. As soon as you start seeing, that's a fold hinge right there, for example. As soon as you start seeing these little fold hinges, you can start to be suspicious that maybe your stratigraphy is being reoriented into parallelism with the second fabric. And the way to measure that first orientation of stratigraphy, which can be very important, of course, is to actually take the enveloping surface of those little crenulation folds, basically draw, you could take a piece of core like this, do exactly what I've got here, draw a little folded tigmatic set of folds here, and then put lines on both sides that bound basically the corridor of that folding. And that's your enveloping surface, and it becomes parallel to the original orientation of stratigraphy. And then the lower right is another beautiful example of rheological contrast, where we have, you can see here, a nice pegmatitic dike, which is totally massive in its core, doesn't look strained at all. But you can see if you had a drill hole across that, you might make that interpretation. But on the bigger scale, it is completely boudinage. So it is seeing all the same strain as the rock around it. It's just deforming differently. And there's your S0 S1. So if we look now at orogenic gold vein systems, here's an important concept of the geometry of these, so thinking bigger picture. Now, it's very common in orogenic gold districts for the mineralization to be localized in and around shear zones, and often you'll have central shear veins, as you see at the upper left, along some of those shear zones at the deposit scale. There's bigger shear zones that control these on a regional scale. But at a deposit scale, some of the more continuous veins, like the one at the lower left, are shear veins, which are polygenerational. They've taken slip along them. They're sitting in the core here of a shear zone. And those have fringing them areas of diminishing strain on either side, where the foliation might change in orientation. It goes from parallelism to the structure in the middle to oblique on the outside. So that's something to consider when you're looking at oriented core. If your foliation ranges in orientation, is it also ranging in orientation with the foliation intensities changing? And you want to be very cognizant of that, because you need to identify your controlling structures. The other thing too is that I've seen a lot of places where people code their veins not on the basis necessarily always of mineralogy, sometimes they are, but on the basis of their strain state. So how deformed are they? In the lower right, you can see an example, for example, here of a set of extension veins, which are pretty unstrained. They're nice and planar still. They have pyrite around them, which is contributing to the grade in the wall rock here. And so some people would call that a late generation of veins, versus over in the middle here in diagram B, the veins in there people would potentially call old because they're highly deformed. They're all boudinage, they're transposed into the foliation here in this shear zone. But in reality, those veins are exactly the same age. It's just that these are forming out on the margins of the shear zone, and these ones in the middle are progressively rotating in the middle of the shear zone. They're connected directly to it, and they're just rotating in the shear zone, and they're getting entrained along the shear zone. So what we're seeing is a strain gradient and progressive deformation. And that progressive deformation is exhibited by these sigmoidal forms you see here of the extension veins that come into that shear zone. So it's very important to recognize these features because it tells you you're approaching the core of a mineralized structure. The density of these veins tells us something potentially about the bulk tonnage grade. You can model densities of these veins. Extension vein arrays are telling you essentially where your sigma 2 orientation is, because the intersection, the tips of these veins with the core of the vein array lies the sigma 2 orientation, which you would also call the vorticity vector, because the veins are rotating around that, and that can become an important ore control as well. It can be a subsidiary ore shoot control, very, very common. So you can see in this extension vein array here in diagram E, essentially the grade is running right towards us in this. The guts of this vein here are right in the middle of that, and it has a horizontal plunge in this case. So very important to understand that when you're looking at orogenic gold systems. Another very, very important feature when you're looking at these systems is the lineations in the wall rock. In orogenic gold districts, oftentimes these deposits are forming in areas where there's a lot of vertical or oblique stretching going on. And often this can occur under transpressional conditions where you're not only taking up translational displacement, but you're also stretching the whole rock mass. Basically, it's a room problem and the whole rock mass is starting to stretch. Often this occurs in late stages of orogenesis, and as a result, a lot of the later stages of veining you'll see in some of these districts form these sheeted sets of extension veins at their tips, which can join shear veins, which then cross more competent units like you see here. This is the Lamaque deposit in Val d'Or in Quebec looking to the west, and you can see these beautiful stacked shear veins that are forming up this rheological contrast, this competent unit, offsetting some of the unit, and then terminating the weaker wall rocks with these horsetails at the tip to form this overall wing crack geometry like you see at the lower left here. And so you can see in these areas, these horsetail tips are just like I talked about earlier with the extension vein arrays. They form intersections with the shear vein and the sigma 2 orientation. You come from these shallowly plunging or gently plunging ore shoots in areas at these tips, and then more continuous shear veins that cross the competent unit and stack up like this. So once you find one of these, they'll stack down, and they stack down the lineations. That lineation you see there, one after another, one of these veins stacks down that lineation. So you can see here some geometry of how some of these shear extension vein arrays can form. They progressively become sigmoidal. A shear vein can break through the middle here, and then you get new veins form on top of them later on. But the early formed veins will rotate. And here's an example in the lower center where we have a shear vein, which retained its orientation because it's taking up the slip. But the extension veins have rotated into vertical here. And so some people might look at this and say, well, hey, that vein there is forming a vein array that's telling us that there's normal displacement on this shear vein. But the problem is that what's happened is that these extension veins have completely rotated. These, you can see this, a lot of these are boudinaged. They would have started off in the same orientation as the veins up here, but they've just rotated over in the core of the vein array. So you can completely misinterpret the shear sense on these types of features if you don't recognize that rotation. And that rotation axis is what we talked about earlier. It's the vorticity vector, where if you have a sigmoidal vein array like this, all the veins rotate in these little shear zones here, basically parallel to that vector and perpendicular to the slip direction on the vein array, creating these plunging subsidiary ore shoots. And there's a beautiful example here in Ballarat of the same kind of a pattern. And in the lower right, here's some real data which shows exactly that. You can see on the far lower right, that's a whole series of extension veins, which I've measured in the cores of sigmoidal arrays and on the tips. And you can see the range in orientation defines a great circle, which is perpendicular to this pole, which is your sigma 2 vorticity vector, which forms an ore shoot control, which you can use in your variography. And on the left, you can see the shear veins associated with that, which also just lie on that great circle as well. So again, subdividing these vein types is extremely important in understanding these patterns. And in a lot of these orogenic systems, is understanding the lineations that these veins make with the vorticity vector is almost as important as understanding the orientations of the veins themselves, because you can see these veins don't necessarily align parallel to the ore body. They're oblique to the ore body. They're stepping up it. They're stepping one after another. You don't want to model your mineralization parallel to them. You want to model your mineralization parallel to the highest density of veins, which is defining the shear zone that ultimately some of these shear veins form along. And here's some of the degrees of rotation you can get in orogenic districts. It can be extreme. There's a wonderful example here that Nick Oliver documented in Brazil, where vein arrays have rotated over and just becomes strung out into all these little lenses. And in this case, you see this was part of a vein, which is offset to here, offset to here. It's been displaced in this left lateral or sinistral shear sense, apparent shear sense here. And it would have started off potentially in an orientation that was perpendicular to that. It started off in this orientation and rotates all the way over and boudinages as it rotates now more and more into the flattening plane, and individual segments just get progressively strung out in the shear zone. So you want to recognize that this is going on, because in the lower right here, you can, for example, again, get the wrong shear sense. Here is, for example, two extension veins. Look how deformed they are. They're all boudinized. They're not planar anymore. And they're sitting in this gray unit, which is a little sandstone. So they're forming because of a rheological competency contrast with the set of finer grained mudstone on either side. These veins have completely rotated. They probably start off in that orientation and they've rotated all the way over. And I know that in part because looking at adjacent outcrops, you can actually see the rotation when you get outside of areas of high strain. So very, very important features to note. Your veins are not always going to be in the orientation they formed in. So the strain axes are not necessarily corresponding with the original stress axes. And another important point here too is that how many of you have read papers which talk about a perigenesis in an orogenic gold deposit, which looks like this? Starts off with pyrite and arsenopyrite, then we get sphalerite, we get galena, we get tellurite, and gold is late. Well, you know what that is? That's a sequence of mineral strength. And you got to be really careful, because what can happen is if you start off with original pyrite and arsenopyrite grains, which are nice, competent minerals under green schist grade conditions, and you have these grains of gold, of galena, and so forth, which behave plastically under green schist grade conditions, and they form impurities in the pyrite grain. If you start to deform the pyrite as that whole vein system is progressively deformed within the orogenic environment, where are you going to nucleate fractures? Right off those impurities. And ultimately, you may have slip along those fractures. The gold, galena, and sphalerite get smeared. And guess what? People say, okay, those minerals are late. They're after the pyrite and arsenopyrite. But in reality, what you're seeing is a mineral strength differential and differential behavior of these different minerals under stress conditions. So what you have to be very careful of is interpreting perigenesis in deformed veins, and go to the tips of the veins, the extension veins. If you want to see the original perigenesis, look at the least deformed part of the vein. So strain gradients. We talked about this earlier around shear veins, very important to try and follow in drill core. Here's some examples where we have some nice pillowed mafic volcanics, which are getting progressively deformed. You can see all these vesicles here that are being completely strung out in an area of high strain. So you can actually code your foliation or your strain intensity. You can do 0 to 3 if you want, weak, moderate, strong, and 0 for nothing. Or you can use more divisions than that if you really want to break it out. You can see on the left here how when you have a strain gradient from moderately foliated rocks here into a high strain zone, that we have a rotation of the foliation into parallelism with the core of the shear zone. And not only that, we have a change in the alteration. You can see that we start to see more carbonate alteration in through here. There's a change in color of the rock here. We've gone from a magnesium tholite to more of an iron altered chlorite assemblage that is closer to the middle of the shear zone in through here. And we also start to pick up carbonate. You can see that in the lower right here, which you see the rusty color. It's an iron carbonate, ferro and dolomite versus calcite on the outside. So there's an alteration zonation that often corresponds with the increase in the strain gradient that you can also model and visually estimate as well. So these are structural features that are not features that you're recording orientations for, but you're recording gradients for, which you can model in drill core. And here's a beautiful example of a strain gradient from moderately flattened and partly stretched pillows here through progressive deformation into a structure that has about 1 kilometer of displacement on it. And in the middle, it's a carbonate, chlorite, muscovite, myelinite with completely transposed veins in it. So that this rock on the right was this on the left. And oftentimes these extremely deformed myelinitic shear zones can be mislogged as sediments. And I've seen this happen in Africa, where a client did not recognize the fact that his controlling structures were all the features that were logged as fine-grade mudstone, siltstone, because they were myelinites. So very, very important to recognize these strain gradients because they're often the controlling structures in these orogenic gold systems. Lineations are extremely important. So when you're undergoing that degree of strain, as I mentioned, often late in the deformation sequence, the cycle of deformation, you have a room problem, and you can often start really stretching your rock mass vertically or laterally, depending on the belt. You can see in this example in the upper right, this is an image of Temiskaming sediments with pebbles in a conglomerate looking down on it. And you can see that that rock looks like it's unstrained unless you start to look at the dip surface here, which is a weak foliation surface. And you can see that all of those clasts are incredibly stretched. So what we have here is what we'd call dominantly an L tectonite. Typically, we'll get both together, a foliation and a lineation. That's what you see here on the left, where Gustav is standing. You can see these beautifully stretched pillows here. In plan view, this is what they look like. They're all round, but these are stretched 4 to 10 to 1 outside the Hollinger ore body. This is a Timmins example. But as you get into the core of some of the ore bodies in Timmins, these pillows get stretched more than 10 to 1. It's remarkable to think of what that's doing to the host rock. That's stretching the rock mass 10 times to 1. Imagine the vertical continuity of the mountain chain above this when this was occurring. It's an incredible amount of stretching. And not surprisingly, your ore bodies, as you see in the upper left, this is in pink, this is a deformed intrusion. In gray, these are ore bodies in the Hollinger mine, and you can see the dominant first order plunge to everything is parallel to that same stretching lineation that Gustav is standing beside. In fact, that's just, that image is taken just above the ore bodies over here. And so we get this intense stretching lineation. But the other thing we get is extension veins forming perpendicular to that lineation, as I showed you before, which then start to form subsidiary ore shoots, which go perpendicular to that lineation. So you'll see in a lot of orogenic gold deposits, if you look at longitudinal sections, you see these two ore shoot plunges. One is plunging parallel lineation, one is perpendicular. And sometimes you'll get third and fourth order plunges where you have rock units interacting with these high strain zones, and this lithology that can create other ore shoot controls as well. If we go now to brittle environments, the brittle environments is the transition at the end of this talk, because I see I'm probably starting to go over time here. But you can see that it's also important to recognize transitions in structures between hydrothermal conduits. This is an example from the Palmarejo district in Mexico, where we have intersecting faults that form probably originally as separate fault strands, but which gradually, as their displacement increased, they joined together and linked in these linkage zones. So these are fault intersections, sometimes fault relays, where faults join together when they're originally on echelon. And in those positions, they can form these steeply plunging zones of high fracture density, which can transmit a lot of hydrothermal fluid. And so what you get is hydrothermal fluid flowing along these to form in the lower right, these beautiful veins. Is this big wide vein zone here right in the corner of this ore body that you see here. So there's been a lot of fluid flow through this highly fractured area of rock. But the other thing that occurs is that the fluid flow also brings in hotter fluids, which brings in adularia quartz alteration, which remains competent and allows that system to keep fracturing as the fault is moving and the fluid flow to continue. However, out here, where you've just got a single fault strand where the fault is moving, but you're not transmitting fluid because you don't have that high fracture permeability, you get lower temperature fluid and you alter the rock, as you see in diagram C, to clay. So you get these areas of clay alteration, which then become so impermeable that you continue to focus the fluid flow in the high fracture density area. So you get a positive feedback loop of fluid flow focus, because your lower temperature alteration out here becomes impermeable clay, and your higher temperature alteration basically keeps maintaining that fracture permeability because of the competent nature of the adularia quartz alteration. So recognizing that the transition in these structures, if you're looking at drill core, from a fault that is clay altered with maybe kaolinite or smectite in it, in this case, an illite, to progressively more and more alteration with the quartz veining here, that is K-feldspar bearing, adularia bearing with quartz, is very, very important. You might model these structures as completely different types of structures, but no, they're not. They're the same structure. They're just changing in character because of proximity to the hydrothermal conduit. A very similar situation here in the Waihi district in New Zealand. You can see here we have a relay developing where we have on-echelon faults that gradually link to one another. These are normal faults, creating this geometry, which some people would interpret as strike slip dilational jog. The problem is that all the kinematic indicators are telling us it's a normal fault. So these are actually what we call a fault relay. This is not a strike slip dilational jog. In fact, fault relays are much more common than strike slip dilational jogs in epithermal districts. And that's a problem with GIS interpretation because you're always taking a plan view look and interpreting everything as if it's got translational like a strike slip displacement, when in reality, you need to look at the 3D component. So in these types of relays, we can form very thick veins in these linkage zones, as you see here. And along strike, in the fault controlled portion of the vein system, we can get these areas where we still have that right alteration. In this case, we have adularia quartz. But instead of forming a vein, we're forming a foliated cataclysite. So this rock is behaving in a brittle manner, but it's forming also a bit of a precious solution foliation in through here because it's the higher temperature conduit with the K-feldspar quartz alteration here. So you're basically allowing the process of precious solution, the lowest temperature ductile form of deformation to occur even in the epithermal environment. But also to note that that foliated cataclysite is only about 10 centimeters wide, and where it changes orientation in those fault relays, it blows up into multi-meter wide veins. So again, another case of the same structure being totally different character depending on when you're in an ore chute or not. And the other thing to remember too in epithermal environments is that there's also sheeted sets of extension veins that come off the fault fill veins. You don't want to code them all as the same thing, otherwise you won't see your fault fill veins in this huge forest of data of all these smaller extension veins. So you want to code your thicker veins, your polygenerational fault fill veins differently from the smaller veins that have different and less complex character to them. So Greg Morrison's talks a lot about that kind of style of mineralization you see in epithermal fluid conduits. So I got a little slide here called joints. What's the point? So if you are doing geotechnical work, joints are very important, particularly in showing you the positions with regard to faults that they may form in damage zones around. But if you're looking at an ore environment, if you're looking in exploration, joints usually don't have anything to do with mineralization unless they have some alteration along them. And a joint that has mineralized material in it, hydrothermal material in it, is not a joint, it's called a vein. That's why we call it a vein. So essentially these are veins, and these fractures that are steep are joints. So in this case, you can see these joints are cutting straight across these mineralized veins. And the reason why joints aren't that useful is because essentially, when you have hydrothermal activity exploits fracture networks. Joints are a fracture network. So joints tend to seal early on in hydrothermal activity. And so generally when you're seeing joints, what you're seeing is late features that are superimposed on the areas of hydrothermal alteration. These are late fractures that are coming in. So don't get hung up on measuring lots and lots of joints if you're not doing geotechnical work. Obviously, if you're doing geotechnical work, it's important, but it's not necessarily going to tell you anything about what your actual hydrothermal system is doing. And getting to the last slides here. So fault zones, recognizing big faults sometimes is difficult. This is an example on the Carlin Trend here of a thrust fault right in the middle here. You see the red hatch pattern is actually the resource model here. And so you can see that there's a major structure coming down here, which has at least 200 meters of reverse displacement on it. Initially, it wasn't recognized in core logging or in the open pit, largely because it's too big. It's so big and it's brittle. It's just a big zone of just silicified and brecciated rock. And so geologists weren't recognizing it, that it was a fault. And the reason is it's an older thrust fault that's been exploited along a limestone unit. So there's been a lot of dissolution by these more acidic fluids in these Carlin systems that has totally overprinted the fault itself. And so what we left with is just a big breccia zone with the gradational contacts that actually defines the position of the fault. But if we can look at the offset units, we can see that, hey, this is following a major older thrust fault. And one way to potentially track that kind of a feature out is to look at the area of broken rock, essentially the intensity of faulting. Obviously, at a seam of gouge, like you see in the middle here, is very intense. But typically faults that are larger aren't just made up of one seam of gouge. They're made up of multiple seams of gouge with a lot of broken rock in between, your damage zone, right? And so you can code your damage zone by relative intensity. How fractures it, what percentage of rock is broken up. It's like an RQD. And using a seam of gouge as the highest intensity, you can actually plot this and look for bifurcating faults here, for example. And not only that, model your faults like a volume rather than a planar feature, because oftentimes these things do have volumes as they open up and thin down or split and splay. And it's actually better to model them as a volume than as a planar feature, because as a planar feature, they have almost no thickness to them, and they also can look very simple and go on forever. But in reality, faults branch, they widen, they thicken, they change orientation. You really want to model these things accurately when you can. And one way to sort out the big ones from the little ones is to do this type of fault intensity logging to really pull these things out. Last slide to show here, I think. That's the last image slide, is just showing you how not to overinterpret. I'm not knocking the geologists that did the interpretation on the left. They did this from drill core and they did their best, but this is a pre-mining example of the same deposit you see on the right. And on the left, you can see there's lots and lots of faults interpreted. And the reason that is they did oriented core. They got lots of little faults in the oriented core with two common orientations. So what they did is they imposed that interpretation on the ore body, which is in black here. And you can see the ore body was all shown as faulted up. When they actually mined this thing, this is what it looked like. What they found was that these little tiny faults really had no impact on the ore body at all. And by over modeling the faults, they made it look like the ore body was much more broken up than it was. So what this can do is this can actually have a negative effect on recognizing the economics of the deposit, because number one, it can reduce the continuity of your mineralized zone. Your interpolation distances drop. You may not get the continuity of grade across faults. Plus, all your engineers get worried about this and basically say, well, you can't mine this underground. There's too many faults here. So you can actually kill a deposit if you model it wrong. And don't forget, as an exploration geologist, when you go to a feasibility study or to a mine environment, the engineers, all they have to base their mining plan on is your interpretation. So if you interpret it wrong, you could have very significant impact on the economics or the perceived economics of the deposit. Both ways. If you don't model your faults enough, you can have huge ground condition issues, or you overmodel the continuity of your mineralization. Your engineers are going to design the mine on the basis of your model. So don't just think I'm going to be an academic and show lots of faults. Prove your faults exist, and even drill additional holes to prove they exist, because the engineers are going to put that into their mine plan. And if you're wrong, guess who's going to get blamed? The geology department. It always gets blamed. So on the right here is another important point, is that faults don't go on forever. So faults typically have a displacement length ratio to them. In the core of a fault, if you have a displacement of 1 meter, typically that displacement length ratio, which is well defined from petroleum work and other studies, is about 50 to 100 to 1. So a fault with a displacement of 1 meter typically will have a strike length of between 50 and 100 meters, and it will not go any further than that. It will terminate, potentially stepping to another fault on echelon, or just end. And so really, small faults often don't go very far, and you don't want to overmodel them. Always keep that in mind. It's very difficult to obviously model that in a lot of current software, because the software wants to take a planar feature and project it to infinity, and you really want to control it. And one way to control it is to model it as a volume rather than a plane. So here we go. Some key points is just really focus on your features that might be useful to your geological interpretation. Don't get hung up on measuring too much stuff. If you go through a section of core that there's not much in the way of structural features, don't try and force yourself to measure things that are there just to take measurements, because then you're going to bias the data distribution patterns. Essentially, you want to reduce also as much notes when you're making core logging as possible. So if a structural feature is repeated over and over that has a common characteristic, you don't need to keep writing about it. You can make a code for it and then code it and put it in there. So basically you want to reduce the amount of notes to maximize the amount of data you gather that you can actually use in a model that's properly subdivided. So again, that's the next point. Proper coding and subdivision of structural features is necessary to define patterns of these structures and to isolate them. Like, for example, I always say is you're not going to, for example, put veins and faults and shear zones in the same column in a structural plot in any way you'd want to put gold, silver, and zinc in the same plot as you're trying to plot geochemistry downhole. You want to isolate each one of those features and model them separately. So use separate columns to model those. You want to model veins separately from late brittle faults. They're not the same thing. They're completely different. You're going to model them differently. You're going to consider their timing differently. The late faults may offset the veins. The veins are going to have their own controls. So separate them out. Unless geotechnical logging is required, try and reduce the amount of joint data. Obviously, another way to record joint data is to look also at the density of fractures, and you can count that. Coding of densities and intensities of veins and foliations can be very useful in tracking shear zones and bulk zones of vein development. And you can use that, like I showed earlier, with the fault intensity as histograms on the downhole trace of a drill hole, and use that as an extra geological parameter to model around gold grade to give you higher confidence in grade distribution in an ore body. And also plot and use the data as the program's proceeding. You want to know what data is useful. You want to know where the errors are. You need to do this progressively, not at the end of the program where you can't go back and check all those errors or start recoding things differently that were really important that you missed because you didn't realize they were important. And this goes back to what Brett was saying the other day about coding your veins appropriately and figuring out the sequence of them. And in areas of ductile strain and orogenic settings, bedding and vein contacts all may be folded and reoriented by progressive deformation. So don't necessarily use them as indicators of paleo stress orientations or necessarily of orientations at the deposit scale if they've been rotated or are on echelon and stepping. So the on echelon extension veins are a good example where we have veins that may not be parallel to ore zones. So you don't want to necessarily model extension veins as being parallel to ore bodies. They can be oblique to them and step up along them. And shear zones too may have foliations that are not parallel to the shear zone itself. So you need to model your strain intensity to track out the orientation of the shear zone. Rheology, very, very important. A lot of orogenic gold systems are localized in certain rock units that are more competent than rocks around them. So modeling those units means you're actually modeling the shape of the ore body often. And the weak units are the controlling structures because they localize the strain. Major ore controlling structures can appear subtle if they're earlier and overprinted by later strain, or have gradational contacts, or they're filled by hydrothermal materials. So you can actually miss major structures if you don't recognize some of these overprinting effects. And one thing that's always helpful is to create an accessible, so all geologists can see it. You can put it in core boxes and put it on a shelf or a series of shelves, build a core library and with different trays for each type of structural feature, lithological feature, and so forth, and get all your geologists to contribute to it so they can recognize and pull out the characteristic features of all the key features. So you have a direct correlation between your codes and your structural features. So new people coming in or people wanting to really refine their understanding of some of the features can go and use this as a reference library and photograph that so you can have that on your computers and online as well. Where underground workings are available or outcrops, go and look at them. This is where you're going to see your 3D component stuff that you can't sort out in drill core. You know, you can spend 10 days, months working on a problem in drill core that you can solve in 5 minutes in an outcrop. Very, very important to go and look at outcrop exposures, underground exposures. I find it a shame so many exploration geologists work on mine sites for decades and they never go underground. They really don't know what they're looking at if they don't do that. Recognize the limitations of drill core interpretation. There's only so much you can do in drill core. but you really need to maximize what you can do with it with some of these types of recommendations. And don't forget, the engineers are going to use your interpretation in their mine design. So it's not just an academic exercise here. This is the real world, and you can actually make or break an ore body if you don't interpret it right. So there you go. Thank you very much.
That was awesome. Thanks so much, Dave.